In this video, I'll be taking the previous year GATE questions from power plant engineering. Let's take on the first question. In a power plant, water density is given as 1000 kg per meter cube is pumped from 80 kilopascal to 3 megapascal. The pump has an isentropic efficiency of 0.85. Assuming that the temperature of the water remains the same, the specific work supplied to the pump is work done for an open system when you consider no losses. Work supplied when you consider no losses, it is minus VDP for an open system. Putting the values here. Specific volume is 1 upon rho, which is given as 1000. 3 into 10 to the power 6. This is P2 minus 80 into 10 to the power 3. I will converting it in pascals. So this gives me minus 2920 joule per kg. This negative sign indicates that yes, we have supplied work done. We have supplied work done. Work is done on the system. That is minus 2.92 kilojoule per kg. Why? Because we have to find the answer in kilojoule per kg. However, do not forget that you have been given an isentropic efficiency of 0.85. So actual work supplied will be work supplied when it is considered as an when the process is drawn as an isentropic process on TS diagram upon efficiency isentropic. Solve this. The answer will be minus 3.43 kilojoule per kg. Minus sign indicates that the work is done on the system. So as you see that 2.92 was also given. So if you forget this isentropic efficiency, you'll get the wrong answer. 3.43. This seemed to be a long question. However, read it once. It's a very simple question. Solve it and you will find that most of the data given in this question is useless. This extra data is given just to confuse you. All you have to do is remember your basics and apply the basic formulas. Do it once. So if you have solved this question, let's read this problem once. An ideal reheat Rankine cycle operates between the pressure limits of this and this, that is 10 kilopascal and 8 megapascal, with reheat being done at 4 megapascal. Data: the temperature of steam at the inlets of both turbines is, this is 500 degrees Celsius, and the enthalpy of steam at the exit of high pressure turbine is this 3185 kilojoule per kilogram, and 2247 at the exit of low pressure turbine. The enthalpy of water at the exit from the pump is 191 kilojoule per kilogram. You have been given this table. Disregarding the pump work, key line, disregarding the pump work, the cycle efficiencies. What is cycle efficiency? Cycle efficiency is net work done upon heat supplied. What is net work done? Net work done is work done by turbine minus work done by pump. However, they have said that neglect the pump work. So neglecting the pump work, we get work done turbine upon Q supplied as efficiency. So the work done by turbine, the total work done by turbine will be the work done by high pressure turbine and the low pressure turbine. So let's draw a TS diagram of this process. This is reheating again. Reheating is done, and the temperature has been given as 500 degrees Celsius. That is equal 500 degrees Celsius. This is T, this is S. something like this. Okay, one, two, three, 4, 5, 6. So 1 to 2 steam expands in high pressure turbine, 2 to 3 is reheating, 3 to 4 is the steam expands in low pressure turbine. So work done, total work done by the turbines will be enthalpy change in high pressure turbine, that is H1 minus H2, plus enthalpy change in low pressure turbine, that is H3 minus H4, and we have to disregard the pump work. Okay, upon heat supplied, now heat supplied will be from 6 to 1, that is in the boiler. Okay, plus 2 to 3 also, because reheating is done. Do not forget this. Many students forget to take the enthalpy change while reheating, so you'll get the wrong answer. Be careful. Okay, so total heat supplied will be enthalpy change from 1 to 6, H1 minus H6, and the heat supplied while reheating, that is H3 minus H2. Okay, now what do you know? The enthalpy of steam at the exit of the high pressure turbine. So this point, exit of high pressure turbine, this is 3185. Oh, this is 8 megapascal constant pressure line. This reheating line is 4 megapascal constant pressure line, and this one is 10 kilopascal constant pressure line. Okay, so this enthalpy is 3185. Next is and 2247 at the exit of low pressure turbine. At the exit of low pressure turbine, this is low pressure turbine, the exit of low pressure turbine. So 2247, 2247. Okay, now we know H2 and H4. We know H2, we know H4, H2. Okay, what, and also we also know H6. Okay, because the enthalpy of water at the exit from the pump is 191, so H6 will be 191. So we also know H6. All we now need is H1 and H3. Okay, what is H1? H1 is the entry to the high pressure turbine, that is the temperature is 500 degrees Celsius. Use this table. The constant pressure line is 8 megapascal, so this value, okay, this value 3399, so H1 becomes 3399. H1 is 3399. Okay, and we need H3 also. Again, the temperature is 500 degrees Celsius, but this time the constant pressure line is 4 megapascal, so you will use this value of H. Okay, so H3 becomes 3446. Okay, put the values of all the specific enthalpies and get your answer as 0.409, but you have to fill the answer in percentage, that is 40.9%. Be careful, you have to fill the answer in percentage. Okay, next question. The thermal efficiency of an air standard Brayton cycle in terms of pressure ratio RP and gamma is given by direct formula. You have learned the thermal efficiency of air standard Brayton cycle is 1 minus 1 upon RP raised to the power gamma minus 1 upon gamma, where RP is what? This is the pressure ratio. Direct formula based question. D. Next question. In an ideal Brayton cycle, atmospheric air, okay, Cp by Cv, gamma is given as 1.4, specific heat at constant pressure is 1.005 is given. The atmospheric air at 1 bar and 300 Kelvin is compressed to 8 bar. Okay, ideal Brayton cycle. The maximum temperature in the cycle is limited to 1280 Kelvin. If the heat is supplied at the rate of 80 megawatt, the mass flow rate of air required in the cycle is, okay, let's draw a TS diagram of this Brayton cycle. Okay, these are the constant pressure lines. This will be more inclined, yeah, This is a constant pressure line of 8 bar. This is of 1 bar. 1 2 3 4. Okay, compression process takes place from 1 to 2. So they have given that the air is compressed from 1 bar to 8 bar and the initial temperature of air is 300 Kelvin. Okay, and the heat supplied is at the rate of 80 megawatt. So let's write Q dot is equal to 80 megawatt, which is 80 into 10 raised to power 6 watt, which is air is used. So M dot H3 minus H2, heat is supplied from 2 to 3. Okay, so change in enthalpy, specific enthalpy in the process 2 and 3 multiplied with the mass flow rate. Okay, so as air is used, we can write Cp T3 minus T2. Great. Now we have to find M dot. We know Cp. Okay, and we also know T3. How? Because they have given the maximum temperature in the cycle is limited to 1280 Kelvin and the maximum temperature happens after the heat is supplied. So T3 is 1280 Kelvin and we also require T2. Okay, now this is an isentropic process for an ideal Brayton cycle. Okay, so T2 by T1 is equal to P2 by P1 raised to the power gamma minus 1 upon gamma. Okay, what is P2? P2 is 8 bar, P1 is 1 bar, T1 you know 300 Kelvin, gamma is 1.4. Can you find T2? Yes, you can. T2 will be 543.43 Kelvin. Great. So now we have found out T2. Put it here. You know Cp. Cp is 1.005. Remember to change it in joule per kilogram Kelvin, because if you equate it with watt, here it is not kilowatt, it is watt. So Cp must be in joule per kilogram Kelvin. Okay, so 1.005 into 10 to the power 3. Okay, let me write it here. 80 into 10 to the power 6 is equal to M dot into 1.005 into 10 to the power 3. T3 is 1280, T2 is 543.43. Solve it, you will get mass flow rate in kilogram per second. Okay, that will be 108.07. check whether in which units you have to fill the mass flow rate. You have to fill the mass flow rate in kilogram per second. So answer will be 108.07. Fill it here. This is M dot. Okay, next question. Steam at a velocity of 10 meter per second enters the impulse turbine stage. Keyword impulse turbine stage with symmetrical blading having blade angle 30 degrees. Enthalpy drop is given as 100 kilojoule in the stage. The nozzle angle is 20 degree. The maximum blade efficiency. Oh, you see that so much data given is useless in this question just to confuse you, because the maximum efficiency of blade for the impulse turbine stage is cos square alpha. You must have derived this formula while studying power plant engineering. It is cos square alpha, where alpha is what? Alpha is the nozzle angle. Cos square 20 degree. I'm not going to derive this formula here. For GATE exam, you learn this formula. That will be 0.833. In percentage, you have to fill. So fill 83.33 percentage. Okay. Pretty simple question. Next is, for a gas turbine power plant, identify the correct pair of statements. Okay, what you do is, in these type of questions, try to eliminate the statements. Like, try to identify those statements that are wrong and you will easily get the right statements. Okay, so the first statement is smaller in size compared to steam power plant for same power output. It is correct. Yes, it is smaller in size as compared to steam power plant for the same power output. Okay. Second point, Starts quickly compared to steam power plant. Yes, it can be started up quickly as well as it can be shut down quickly also, like a diesel engine. Okay, so it is correct. This is correct. Works on the principle of Rankine cycle. No, it works on the principle of what? It works on the principle of Brayton cycle. Okay, and good compatibility with solid fuel. No, this is wrong. Uses any hydrocarbon fuel. Okay, from high octane gasoline to heavy diesel oil, and so this statement is also wrong. So you get the answer as PQ, because you have to identify the correct pair of statements. Sometimes they also write here that you identify the incorrect pair, and some students, what they do is they mark the correct pair of statements. Be careful. Okay, next question. Steam with specific enthalpy enters an adiabatic turbine operating at steady state with a flow rate 10 kg per second. As it expands at a point where H is this, 1.5 kg per second is extracted for heating purposes. That is, it is a question of regeneration. Okay, the remaining 8.5 kg per second further expands to the turbine exit where H is this. Neglecting changes in kinetic and potential energy is the net power output of the turbine. It's a very simple question. All the enthalpies on all the specific enthalpies have been given, and all you have to do is find the net power output. Okay, let's draw a rough TS diagram for this regeneration process. However, it may be open feed water regeneration system or closed. I am taking that it is open feed water. Okay, so okay, so they have said that it enters with an enthalpy of 3214. Okay, this is 3214. The flow rate initial is 10 kg per second. As it expands at a point here, the enthalpy is 2920 kilojoule per kilogram. Specific enthalpies is extracted, some mass is extracted, and the remaining expands to the turbine exit where H is 2374 kilojoule per kilogram Kelvin. Okay, so power output will be m dot initial enthalpy change in the first part when 10 kg per second of steam was supplied will be this 290 plus m dot final after the steam has been extracted. 1.5 kg per second of steam has been extracted. This will be 2374. This will be net power output. M dot I is what? This is 10. Solve it. Plus m dot F is what? 8.5. Solve it. You will get the answer as 7581 kilowatt. You have to find the answer in kilowatt. Okay, next question. As I mentioned, TS diagram. Yes. Okay, so the next question is, steam enters a well insulated turbine and expands isentropically throughout. Great, this word. At an intermediate pressure, 20% of the mass is extracted for process heating. Okay, again a problem of regeneration, and the remaining steam expands isentropically to 9 kilopascal. This is the data. Inlet to the turbine, you have been given pressure, temperature, specific enthalpy, and specific entropy. Intermediate stage specific enthalpy is given, and at the exit of turbine again some properties are given. Okay, if the flow rate of steam entering the turbine is 100 kg per second, then the work output in megawatt is. Okay, do you want to try it yourself first? It's a good question, so try it yourself first before seeing the solution. So if you have tried it yourself, let's construct a rough TS diagram. again this process to have a better clarity of the process. This is isentropic process. Okay, so 1 2 3, this is a straight line. Okay, this is a straight line isentropic process. This is 4 5 6 and this is 7. Okay, so work output, what will be the work output? Work output will be m dot initial in megawatt. Okay, m dot initial to change in enthalpy from process 1 to 2 when whole of the steam was expanded. Okay, plus m dot final when some part of the steam has been extracted. Okay, the initial value of m dot I is 100 kilogram per second, h1 minus h2, and how much mass has been extracted? 20% of the mass has been extracted. So what goes in the process from in the process 2 to 3? 80 kilogram per second, h2 minus h3. Okay, now do we know h1 h2 h2 and h3? Let's see. So inlet to turbine, yes, we know h1. Inlet to turbine 3486, we know h1. This is 3486. Do we know h2? h2 is the intermediate stage enthalpy where the steam has been extracted. Yes, the enthalpy has been given, which is 2776 kilojoule per kilogram. So this is also known. Here it is also h2 2776. Do we know h3? h3, exit of the turbine. It is hf has been given, hg has been given, sf sg have been given, but h3 has not been given. So this you have to find out by using these properties. Okay, now h3 is equal to hf plus x hfg. Yes, what is x? X is the dryness fraction. Okay, now hf is 174 plus x, we don't know dryness fraction. Okay, and we don't know h3 also. hfg is hg minus hf, hg minus hf. hg is 2574 minus hf 174. Okay, so now we don't know dryness fraction, so now we have to find dryness fraction. How can we find dryness fraction? This steam expands isentropically, so S1 is equal to S3. This is correct. And do I know S1? Yes, I know S1. Inlet to the turbine specific entropy is 6.6 kilojoule per kilogram Kelvin. So S1 can be written as 6.6. Whereas S3, do you know S3? No, you don't know S3, but you have been given with SF and SG. Great. So S3 can be written as SF plus X SFG. Okay. Now that implies 6.6 is equal to SF. What is SF? SF is 0.6 kilojoule per kilogram Kelvin plus X is the dryness fraction. SFG is SG minus SF. SG is 8.1 minus SF is 0.6. Okay. Can you find dryness fraction from here? Yes. You will get the dryness fraction as 0.8. Okay. Now put this dryness fraction here. What you get? You get H3. H3 you get as H3 is equal to 2094 kilojoule per kilogram. Great. Now you've got H3. Put this H3 here. What you get? You get the work output. And whose value will be 125.5 megawatt converted in megawatt. Okay, because you have to fill the answer in megawatt. So yes, this was a nice question. Okay, thank you.